Okay, welcome to lecture number 8, which is the last lecture in this course in that particular year, but of course next year on the 6th Epiphania, yeah, in my home. And this is a holiday, but unfortunately we're here in Protestant area, so we have to work. Yeah, I also have to work, even though I'm usually, for me, this would be a holiday. So this time it's the last lecture in 2025 in this course on lattice Blotzmann method. And today is a very central lecture to this course, namely the asymptotic analysis. So this is more or less something that the entire theory is kind of built around. So it's a very central thing where we put also everything together which we already learned regarding the Taylor expansion, yeah, but we'll now do it in more stringent and more in depth. So what we are going to do is we will have a particular example for this, namely we derive the equivalent partial differential equation that is solved by the lattice Blotzmann method, and we have to be specific here. We do this for the D2Q9 lattice BGK. So this is the simple lattice Blotzmann method that we have already introduced. This method can also be used for more complicated lattice to analyze other lattice Blotzmann methods. Then you have to modify the specific card that we're applying here a little bit. Okay, so I try to be very self-contained, and therefore I'll repeat something. Yeah. So I guess we have now already understood that we have this. Okay, it's not very beautifully drawn, but this is our velocity set with the definition of the velocities in Miller indices. Yeah, so this here is F111, F10, F1 minus 1, F minus 1, minus 1, F minus 1, 0, F minus 1, 1, and here there's also an F0, 0. So this is our D2Q9 velocity set. And that means this, if we have the populations Fij with Ij being an element of minus 1, 0, and 1. So this is a so-called tensor product lattice. So for this, we want to solve the lattice Blotzmann equation. And the lattice Blotzmann equation, in case I've not made it clear so far, lattice Blotzmann equation is this discrete equation that will give the number 8.1. We put, for convenience, this is not necessary, but later for convenience, will be useful to put everything on one side and say 0 is equal to. So, and here we have the pre-collision state Fij at position x, and so I remind you, we are always using, we are always assuming that these populations exist on the halfway in between lattice points. Yeah, so we'll move them according to their direction I and j. So these are the unit vectors. So they exist halfway in between, and they exist halfway in between time steps. So this is next neighboring node and next neighboring time step halfway towards this, right? And this is equal to, and because I want to put everything on one side, I said this is minus Fij, the post-collision state before. So now here everything the same, just with a minus. And also this has been half a time step before. So you see, in total, this is one time step in between and one grid spacing in between. Yeah. So this thing is what we call the lattice Boltzmann equation, and this is basically for this given discretization, this is always true, independent of the collision operator, for example. Yeah, because we just compare the post-collision state and the pre-collision state, and we don't say anything about how they came into existence. Yeah. So when okay, later we have to use the BGK equation, because the BGK equation is how we actually do this update. Yeah, so the BGK equation, and again, there can be other collision operators that do things in a different way, and then we have to replace this. So we'll call the BGK equation 8.1, and here we have the post-collision state. Now this is at x and t, so this is at the position where the collision takes place. So, and here I write the difference. Okay, I could have written this differently, but let's say the difference between the pre-collision, the post-collision and the pre-collision. This is this single relaxation time update, where we have a relaxation operator omega, the equilibrium minus the pre-collision state. Okay, so this is the BGK equation, and you know this equation, that if you, I mean, in practice, when we write it in the program, we write the post-collision is equal to this, so we put this on the other side plus this part here. Yeah, so this is how we will program it. So, and then we have already seen that we can use a Taylor expansion of the lattice Boltzmann equation in order to do an analysis, and lots of people also stop there, just do Taylor expansion, and we can do a lot with just Taylor expansion, but I will briefly mention why we'll go a little bit further than that. So Taylor expansion of the equation 8.1. So if we do a Taylor expansion, we always have a development point, and our development point is x and t. So this is the point where the collision takes place. Yeah, and so this is the lattice node at collision time. So now this is an important equation 8.3, where now for convenience, everything up here in 8.1 is of course 0. Therefore I put 0 on one side, and then I Taylor expand. I write only one sum because the equation is getting long enough anyway. Yeah, I write only one sum. For the Taylor expansion, you see we are now in 3 dimensions, basically because we are in 2 spatial dimensions and we have 1 temporal dimension. So we have to do a Taylor expansion in 3 dimensions. So we'll have them in M, N, and L. And I will use M for T, N for X, and L for Y. And all of them, of course, start with 0 and go to infinity. Then we have the usual Taylor expansion stuff in the front. So we have 1 over m factorial, n factorial, L factorial. So this comes from the prefactor of the Taylor expansion. Then we have to have the distance that we move from our development point. So that is delta x. Delta x half, and we move delta x half in x and in y. Yeah, this is why I take the liberty to not make it too long. I just say n by the power of n plus L, because we're going both dimensions the same distance. And we have delta t half only once, of course. Yeah? Yes, you are right, M. Thank you. It's written correctly in my. Okay, I should take this in front, yeah, so that I don't get confused myself. Okay, now I start with I used shorthand for the derivatives because they again get long. So this is the nth derivative in t, the nth derivative in x, and the Lth derivative in y. And then you see, we have here I and j. Now these come here. I by the power of a. Yeah. So basically, not by the power of a. What nonsense am I writing? By the power of n. Why do I have this here? Okay. I by the power of n. So basically we have here delta x, yeah, times I, and unit length, yeah, unit length goes together. So the direction goes into the derivative, yeah. So this is where ex goes, because it's the directional derivative, yeah. So and then we have I delta x half and y also delta x half, but then with L. This is why I put with L. This is why I put both of them up here. Yeah. So J and L, and this into Fij. I'm not writing the coordinates again, but this is the expansion of this thing here, right? So then we also have to expand the other thing. When we expand the other thing, we first have to recognize that there is a minus in front. Then the distance that we travel, or that we are away from the development point, comes here with a minus. So this is now significant because we do this to, okay, I mean, why do I say it's significant? I mean, it's just minus I, yeah, by the power of n. So you will see this changes sign depending on n, yeah. So this is what we later observe, and of course minus j by the power of L, and this goes into the post-collision state Fij asterisk. Okay, so nothing magically here, hopefully, right? This is just the 3-dimensional Taylor expansion. So in order, I'm going to call this thing T, yeah, so that's because it's a little lengthy. Anything unclear with this? minus sign with the delta t half. The minus sign with this delta t half is, yes. Yes, very well. Yes, yes. I've not, okay. Minus and this with m. Thank you. Okay. You see, I need to put this here in a space where I can read it better. Yeah. That's true. Thank you very much. So minus 1 for t, of course, 2. So I have been told by some people. Okay, I should say anything else? No. Okay. I have been told by some people that I'm making here assumptions which I cannot do. Taylor expansion, of course, assumes regularity up to infinity. And this may not be true. Okay, so but we do it anyway. Yeah, so we do it, and if it breaks, it breaks. Yeah, so if it does not break, it, I mean, if the thing is regular, if we get a solution, it will behave that way. Okay. Or putting it this way, now we are engineers, we're not mathematicians. Yeah, we just want to know the answer. Yeah. So what can we do with this? So some people use this thing as is in population formats, and we want to put it into moment format. And they're very important that this has to be done with raw countable moments, so not with central moments. I sometimes observe very good and interesting students seeing this and thinking, okay, let's do this in central moments instead. That doesn't work. Yeah, so don't try to get too clever. I can later say, well, I can later explain why it does not work this, but it works with raw moments. So the raw moments M, A, B, we've already, of course, introduced this from -1 to 1 for that particular lattice, Fi, j, I by the power of A, j by the power of B. And for post-collision moments, we have the same. We just indicate this by an asterisk. I, j -1 to 1. Fij, the post-collision part, I by the power of A and j by the power of B. So, as we already discovered, we are not solving for either pre-collision or for post-collision, but we are solving for the average between both of them. So we'll have to introduce also this average moment, MAB, which again is the same. And here we just have Fij plus Fij after collision, and we take the the average of the two. So, and when we take this average of the two, we also have to define something else, because now, I mean, we cannot turn one variable, two variables in one variable. Yeah, we have to, when we have the sum of them, we also need the difference of them. And the difference we call omega AB. And so this is related, you see, this is what in the Boltzmann equation is the collision operator. Yeah. So because this is the difference between the pre-collision and the post-collision. So the other way around. It's the difference between the post-collision and the pre-collision. So it's the change. It's the change due to collision, yeah, but for a moment, not for the distributions. Yeah. So again, we have this I by the power of A and J by the power of B. So this is the moment of the change during collision. Yeah. So these things are the variables that we are going to use in our expansion now. And the idea basically is that up here in equation 8.3, we have an equation of populations. And as we can take moments of the populations, we can also take moments of the equation of populations. Yeah, so we can take the moment of the, moments of the lattice Boltzmann equation, and we can take the moments of the Taylor expanded lattice Boltzmann equation. And that's what we are going to do. So we'll take moments of 8.3. Basically, the idea is so 0, yeah, so because this is the expansion, we take moments over the sum over ij from -1 to 1. And here we have this entire equation, and we multiply this by IA and JB. Yeah. Basically, okay, maybe I do a small change in nomenclature, yeah, because we have here I and J everywhere. I call this thing here T, I, and J, right? Yeah, because so, and then obviously this here is T, I, J. Yeah, and of this I take the moments, and obviously all of that needs to be 0 because the thing itself is 0. Yeah. So doing this, unfortunately, we get longer equations today. Yeah, so always write to one side here. So we'll still have the sum over I. Am I actually audible very well? We have I, J from -1 to 1. So this is what we have for the moments. Then we have the sum over M, N, L from 0 to infinity. And here we have delta x half, n plus L, delta t half by the power of n. And okay, I made a mistake in my writings here, so I have to repair this ad hoc. So we have m factorial, n factorial, and L factorial. So we have dtm, dx, dxn, and dyl. And here we have fij. So now what happens now? Because we multiply the entire thing by I by the power of A. Yeah. So we'll have now the power n plus A. Yeah, because previously we had by the power of n, and we multiply by I by the power of A. So the same thing goes here in JL plus B. And now for the rest, it's a little bit more complicated, yeah, because we have minus I, but we multiply with I. So the way we do this is, okay, first we write the minus, then we write -1. We keep this at n, and then we have I by the power of A, and then we have -j by the power of L, and j by the power of b. And okay, the ones that I forgot before, minus 1 by the power of m, by the power of m, and fij after collision. Okay, is this right? I by the, okay, so that looks like, okay, so this looks like a 1, right? Sorry. I by the power of n, minus I by the power of n, yes. So the thing here can also be written as I by the power of n plus a, j by the power of l plus b, and then minus 1 by the power of m plus n plus l. Okay, it's not nicely written here, yeah, but I hope you understand. You can read, yeah. So it's we take the minus 1 out and put it to the power m plus n plus l. So that would be the same thing. So we have, so far we have not really changed anything. Okay, now comes the, so this is the Taylor expansion, and you can do a lot with the Taylor expansion already. But now we also want to do another expansion, and this is called the asymptotic expansion. And for an asymptotic expansion, we require something that's called the smallness parameter. In smallness parameter epsilon. Okay, I think that this thing is a good idea, but good ideas always get criticized. So therefore, I mean, first the question, why do we do anything more than Taylor expansion? And there are people out there that just do Taylor expansion and are very happy with this. And I also sometimes use just Taylor expansion for specific problems. Yeah. So, but sometimes that may not be enough. Okay, there is one more technical point, maybe, that's the regularity, that we can somehow apparently circumvent with this, at least if we do it in the right order, regularity of the series. So maybe, and actually, so they should be regular up into infinity. So this is in question, or somebody could say, okay, this is actually not true. If you remember the exercise that we had the programming session after the lecture last time, we saw that we compared delay bounce back and no delay bounce back. And our observation with the no delay bounce back was that we see these oscillations. And still, even with these oscillations, if we had enough resolution, we could obtain a reasonable result. Now, in principle, mathematician could come to you and say, so you have oscillations, you do a Taylor expansion of something that oscillates. Actually, this is a discontinuity at the high frequency level. So your Taylor expansion does not exist, okay? So basically that you can put all of this in question, yeah, because you're expanding something that does not behave regularly. Even though you can still extract the right result. And something that I did not show, and I showed this. Okay, I have not shown this for 10 years or so, but what I've shown previously in these circumstances is also when you have these oscillating results. So you especially with the lid-driven cavity problem, so you can choose a resolution where you have very high frequency noise, and in particular in the pressure in the second moments. And even if you don't refine the grid, you just do this simulation with these oscillations, and what you then do, you apply a low pass filter. Yeah, you apply a low pass filter, and if the low pass filter is strong enough, it will dampen out this noise, the noise which is much stronger than the actual solution, and out comes, only post-processing, out comes the correct solution. Yeah? So the correct solution is somehow hidden behind the oscillations. Yeah? But the oscillations would actually make the Taylor expansion impossible because you have not a regular, if not a continuous function. So that's more technical. We do it anyway and it works anyway, and we are not mathematicians. There's something else. Because another engineer, who is actually not questioning this, I was just questioning, well, they actually looked at my lectures because they are online, and said that, okay, you derived the Navier-Stokes equation already with Taylor expansion from, and here we do a little bit, we trick a little bit something, because it's not, there's a little bit a problem. With this, so you can do Taylor expansion. So Taylor expansion is very powerful in separating the result from the error for linear problems. Now, obviously, the Navier-Stokes equation is not linear, and the lattice-Blotzmann method for the Navier-Stokes equation again is also not linear. Yeah, and in the Taylor expansion we don't have necessarily a very good measure for the asymptotic behavior of these nonlinear parts. So this is something that with asymptotic expansion gets much more. I heard that if you write something with hyphen, you implied that this was written by artificial intelligence. So that I'm going to use this now. Yeah, I mean, this is in applied mathematics. People absolutely love linearity. Yeah, all their tools from Neumann analysis and all of these things, they are all for linear parts, for linear things. And if something is non-linear, they do linearization, and that may be a good thing. But I mean, one thing you have to remind yourself when you're in fluid mechanics, 99% of all of these things disappear and doesn't work. Even linearization, if you think about it, you have a Reynolds number. Yeah, and the Reynolds number is the ratio between the non-linear part and the linear part. Yeah, advection versus diffusion. And once this is larger than 1, it means that the nonlinearity is stronger than the linearity. And usually, I mean, there are applications for Reynolds number 1, but usually we have Reynolds number in the, billions. Yeah. And so this you always have to keep in mind if you linearize anything with fluid dynamics, yeah, the nonlinearity is so much stronger than the linear parts. Yeah, all of this is very questionable, and most of these things don't work. So asymptotic analysis works with nonlinearity. That's a good thing. Okay, what is all of this now about? What do we do instead? We are not doing I should say we are not doing anything instead of the Taylor expansion. We use the Taylor expansion. We just do something on top of the Taylor expansion. Yeah. So Taylor expansion will always be present. And now we have to go very briefly to the very, very basics of numerics. This is something when you go to my lectures, is almost in all of my lectures. So what is actually numerics? We need this. So numerics always, most of them, there are the exceptions of stochastic methods like Monte Carlo shooters. They work a little bit different, but most of the numerical methods somehow go around something that's called the smallness parameter. Yeah, and mathematicians like to call the smallness parameter h, and physicists like to call it their smallness parameter epsilon. But anyway, you have to identify what your smallness parameter in reality is. So, and this thing epsilon, so I'm not a mathematician, so I call it not h. This is a discretization dependent smallness parameter. So the easiest examples that you would usually come along is you have a grid size. So the size, the grid spacing, or you have a time step. Yeah. So in a usual Runge-Kutta method, you have a time step, and the length of the time step is your small parameter. Everything works only if this thing is small, and you get convergence when you make this thing smaller. Yeah, and this is how we define a numerical approximation. So we have a numerical approximation. So say our approximation is called phi. And this phi has some independent variable. So this is usually what we have, the space-time, whatever. Yeah. And it's a function of the smallness parameter epsilon. So this phi is a numerical approximation. What we actually want to know is the function f of x. And the problem is that f of x is of that kind that we cannot solve it. Yeah? That we cannot just solve it. So therefore, we replace f of x with phi of x and epsilon, with the difference that phi of x and epsilon is something that we can solve. Yeah, f we cannot solve, but it's what we want to know. And phi we can solve, but it's not f. It's not f because in addition to being f, it also comes with an error. And this error can hopefully, or this is our assumption, which may not always be true, yeah, but this is our assumption, that we can expand, we can make a series expansion of this error in the smallness parameter epsilon, and with constant ease. So we have here the approximation. We have here the true function that we want to evaluate. And we have a series expansion of the error. So now, actually, you can always say that something is something plus an error. Yeah. So in order for the method to make any sense, so that we call them consistent. They are consistent if the limit of our smallness parameter going to 0 for phi, x, and epsilon is f of x. So if the error disappears for epsilon going to 0, then we say that that the method phi solves f, right? So very, very basic, but very, very important. Okay, let's write this down. Numerical approximation phi of x and epsilon is the truth plus I don't know, is it or n hierarchy? I don't know. Hierarchy, okay. I use too many n. Hierarchy of error terms, and they are separated by powers. So this is how we just expand the error in power of epsilon. By the way, this is again a Taylor expansion, yeah, around epsilon being 0, yeah. So now, how do we get this into our method here? So we say that by evaluating our lattice Blotzmann method, we get a moment MAB. So this is what comes out of our numerical approximation. So this is phi, right? But we don't want to know phi, we want to know f. So now let's say this can be expanded from n equal to 0 to infinity into a smallness parameter by the power of n and m a b, and here we write an order. Yeah, so this is not an exponent. This is why I put here the brackets to distinguish. This is an order n, and we also can expand this omega thing. And I mean, this can be the overbar version or not the overbar version, doesn't matter. It can be plus pre-collision, after collision. So we do the same thing here from 0 to infinity, epsilon by the power of n and omega a b to the nth order. So now the important thing here is to say that this here, so this is the expansion of our numerical solution with these MAB to the nth order and omega AB to the nth order. They are not functions of epsilon. So is this, okay, so this is important. Is this clear or is there any confusion? So it is clear because all the dependency is in this expansion. So these things are constant, yeah? So, yeah. So this, of course, applies also to the macroscopic variables, which are, of course, moments. So we have the density and velocity. we can do an asymptotically expanded. So we have the density rho. So the density rho, when I do not write any order, then this is the thing that comes out of the simulation. So that's the numerical result, which is not the result we are looking for. We are looking for the result minus the error, right? So, and now we have here an order 0 part of this. We have an epsilon times order 1 part, epsilon square order 2 part, and this is going on. And the same thing is with the velocity. So this again is the numerical outcome. We have here u by the 0 order plus epsilon u by the first order plus epsilon square u by the second order, and so on. Okay, so we can expand our macroscopic variables, and only one of them will be the solution we are looking for, and all the others are the errors. Yeah? Okay, now you notice that fluid dynamics is not straightforward, right? Yeah, so now we have a kind of a little bit of problem. Namely, this expansion, I mean, for this sort of expansion, okay, we could potentially expand in several smallness parameters. Yeah, that would make our life pretty difficult. We want to expand in one parameter. But then, in reality, we solve a partial differential equation, and a partial differential equation, by definition, has several independent variables, and for each independent variable, we actually have a smallness parameter. So the only thing we can do is somehow couple them, right? Yeah, and okay, it's easy to couple x extension and y extension, but here we have x and t. Yeah, we have time, so we have two numerically small parameters, delta x, and we have delta t. So, and now you have to couple them, and there are, of course, infinitely many ways how you could couple them. And there are two obvious ways of coupling them. I guess you can give me two obvious ways I could couple them. Or at least you can give me one obvious way to couple them. Hmm? Yeah, or is proportional to. I mean, is equal to is a little bit, from a physical point of view, a little bit difficult because they have different units. But say we say if we make x 10 times smaller, we make delta t 10 times smaller. That would be a very reasonable assumption, but unfortunately, it is not a good assumption, as we'll see in a minute. So, yeah. We have different choices for epsilon is possible. So we'll discuss two obvious. There are infinitely many, but we'll use only, usually there are only two that have particular applications. But both of them are important, and today we will use one, and next year we'll use the other one for another purpose. So there are two obvious choices. So the first one would be, as you said, delta x is proportional. Okay, I'll write. I'm using this lazy here to say this is proportional to. Both of them are proportional to epsilon. So what that would mean is that delta x by delta t, that would be constant, yeah? And when they are constant, that would mean that the speed of sound, which is a constant in in lattice units, the speed of sound is invariant under scaling. So the speed of sound is invariant under scaling, and this is where the name of this procedure is drawn from. It's called acoustic scaling. It's called acoustic scaling because the speed of sound is invariant under scaling. So is this a good choice? I mean, sometimes it's a necessary choice. Whenever you want to do acoustics, aeroacoustics, then this is even a necessary choice. Yeah. But let's look what are the consequences of this. We have in the Navier-Stokes equation, because it's not entirely incompressible, we have two dimensionless numbers. You see, this is related to having two. Okay, I have to. I'm back in a moment. So this will be forever on the recording. I don't spend any time cutting things out. I'm too lazy. So two dimensionless numbers in the Navier-Stokes equation, right? We have the Mach number. I mean, when we speak about speed of sound, which we have, then we obviously have a Mach number. So Mach number is, I write the dimensionless stuff with an asterisk here. It's dimensionless velocity divided by the speed of sound. So this is a physical, the with dimensions, physical velocity. Physical velocity. And of course, we have the Reynolds number. So Reynolds number is, we have again the physical velocity, we have a physical length scale. And we have a physical viscosity. So this physical viscosity is the speed of sound 1 over omega minus 1/2, and this into delta t. And this is, yes, this is the viscosity. So that means we can write our Reynolds number in the following way. We have a Reynolds number U asterisk times L asterisk divided by CS square 1 over omega minus 1/2 into delta T, which basically we can also express by the Mach number. Yeah, we notice that our Mach number is now constant, because the speed of sound is independent. I mean, okay, it's scale invariant, yeah, not dependent on our scale. L divided by CS. So I'll replace Mach number. I replace U and one of the CS by Mach number. Yeah, so this is why we don't have a square here. 1 over omega minus 1/2 into delta T. Now, the Reynolds number is to be kept constant. In our simulation. So, I mean, independent of the scale. So independent of the grid spacing. And the time step. And if somebody here listens, maybe later on the internet, yeah, and thinks about Chapman-Enskog expansion, which you'll find in most of the lattice Boltzmann books, or when you go to another course on lattice Boltzmann that's not given by us here, then you will probably come along the Chapman-Enskog expansion, which we do not do here. In the Chapman-Enskog expansion, this is different, because the Chapman-Enskog expansion is an expansion that derives that was invented to show the transition from the kinetic theory to the Navier-Stokes equation, or the Euler equation and the Navier-Stokes equation and the Burnett equation, and so on. And this is very often used also for the lattice Boltzmann method, but it's not actually derived for the lattice Boltzmann method, so you're misusing it a little bit. In the Chapman-Enskog expansion is an expansion where you increase the size of the system. By that, you scale up the Reynolds number. So in the Chapman-Enskog expansion, the Reynolds number increases. So you're not, and this is the case because you're not shrinking the atoms, right? Yeah, so because you think about physics, the physics has a finite size, you're not shrinking the atoms. Yeah, so you're increasing the size of your system, and you see what is the result of this physically on the large scale. So in numerics, this is why I don't teach this here. I just mention it so that you don't get confused when you get along. In numerics, we are not interested in scaling up our problem. Our problem has a fixed size. We are interested in scaling down our discretization. That would be like in the Chapman-Enskog expansion, we are making atoms smaller, which does not make physical sense, but in numerics it makes sense, okay? So now this is here a difference, yeah? Chapman-Enskog, upscaling of Reynolds number. Here, this asymptotic analysis, Reynolds number is fixed. Very important point here. So in the decision that we made, we have the Mach number, and CS would be independent of delta X and delta T. So that would mean, say if we take the stuff that is independent, so the Reynolds number should be constant, yeah? So I rearrange this here a little bit. Yeah, so I'll put CS on the other side because it's also supposed to be a constant. I put the Mach number on the other side because it's supposed to be a constant, and I put L to the other side because it's supposed to be a constant. And then I have 1 over omega minus 1/2 and delta t. And then I can solve this for 1 over omega. I'm not bothering with anything else. So Mach divided by Reynolds number CS, 1 over delta t plus 1/2. And this thing here is scale dependent. So what does this mean? That means that our omega is scale dependent. So when we choose a different resolution, when we scale our system, we have to scale omega. Is this a big deal? Okay, write it down. In acoustic scaling, so acoustic scaling, again, is the one where these things are proportional to each other. Omega is a function of epsilon. Okay. Now, if you look in the literature, in particular, yes, so there's a French group doing this a lot, but also others, maybe. This is usually ignored. And I mean, this is really fascinating because I'm in this business for 20 years now, and this discussion goes on for 20 years. And when you meet these people, you get them to agree, but they have forgotten 10 minutes later. So this is, I just warn you, yeah. The dependency of omega on delta t in acoustic scaling is a persistent error in the literature. I mean, mathematicians, applied mathematicians are interesting people. They just say, okay, you know, we assume it is constant, yeah. Yes, you assume it is constant, but it is not right, yeah, because then your Reynolds number, you're not solving the same problem. So, I mean, this is a central problem. So you cannot, when you have this this equation, because it looks harmless. So you put in what your program does, but if you want to expand it and look at the asymptotics of this, you have to notice that you cannot use the same omega for the same resolution. So you have to expand this too, yeah, and that's yeah, I mean, this can be done, but then it should be done. So if you do, and we are going to do this in a later lecture when we come to grid refinement. Here, let me just write this down. In acoustic scaling. So the lattice speed is, okay, so what does it mean? The lattice speed, because the lattice speed is, okay, the lattice speed is delta x by delta t, yeah? And this thing is not asymptotically small. So delta x by delta t is constant. So this is a big problem because LBM does not converge under acoustic scaling. And then I could open a bracket because people make it converge by using assumptions, yeah, but they are usually not true. See, we have this finite velocity lattice, yeah? So whenever our velocity is not zero, we do some sort of error. And if the velocity that we use in that particular simulation will not be scaled down together with our smallness parameter, this error will not decrease. And because the error will not decrease, the method does not converge. It does not converge. Yeah, lattice Boltzmann does not converge in that scaling. So therefore, there is something that somebody called, so for example, Paul Dellert, when I talk about diffusive scaling, he said this is cheating. Yeah, okay. I mean, yeah, you could say if you are people, okay, you could say people use acoustic scaling and they just choose a velocity that's small enough and say, okay, it does not converge when I make it small, but I'm fine with this. Yeah. So I mean, you could, if you are happy with your method not converging, you can use asymptotic. You can use acoustic scaling. There actually is a scaling that makes the lattice Boltzmann method really converge, and this is the diffusive scaling. So, and in this has the convenience that we keep omega lattice scale independent, and if this is true, so if you use this diffusive scaling, we do not need to expand omega, because omega will be independent of the scale. Let's see how this is done. So let's look again on our Reynolds number. So the Reynolds number is these physical things, U star, L star, which are given physical quantities, so they are not scaled. They go 1 over divided by C S square 1 over omega minus 1/2 into delta t, and we demand, because we are not doing Chapman-Enskog expansion, we demand that this thing here is constant. And now let us look at the CS square. The CS square, we have already used this last time. The CS square is, of course, something, I leave a space here, delta x square by delta t square. So these are the units. And here we multiply this with theta, where theta is, so theta is the numerical value of this, 1 over square root 3, yeah. That is called the dimensionless temperature. Okay, the speed of sound is related to the inner the microscopic kinetic energy, and the microscopic kinetic energy is of course related to the temperature, yeah, by the Boltzmann constant, but we forget about the Boltzmann constant, yeah. So when we want to write, so the point here is I want to take the dimensions out of the CS, yeah. So this I do by writing a dimensionless number here, and if I do this, I can write my Reynolds number as U star L star divided by theta delta x square by delta t square 1 over omega minus 1/2, and then I have to multiply this by delta t. And now I want omega to be constant. And this is, if you divide this, you see that this would be the case that if delta x square is proportional to delta t, right? So, and then if this is the case, this has a consequence that CS is the square root of theta delta x by delta t. But now, because delta t is proportional to delta x square, we have this being theta epsilon by epsilon square. So we make epsilon is proportional to delta x, right? Epsilon like this. So this becomes 1 over epsilon, which implies that the limit of epsilon to 0 CS is infinity, yeah? And of course, also the limit E epsilon equals going to 0 for delta x by delta t. So the lattice speed is also infinity. Yeah. So if your speed of sound and your lattice speed is infinity in the limit, then your lattice velocity is small compared to that infinity, right? And therefore we have convergence. Yeah. So right, I want to write this down. Simulated velocity is now asymptotically small compared to the speed of sound. And the lattice velocity. So, the one thing is we cannot do acoustics. The Mach number is not scale invariant. So the speed is u. Okay, so this is the physical speed. Here u is the numerical speed that goes into delta x by delta t, and delta x by delta t is, so this here is dimensionless. And this here has the units 1 over, this basically is 1 over epsilon. So I'm talking too much here, but maybe I hope you come to listen to me anyway. So our u, the solution of the Navier-Stokes equation. No, this is not the solution of the Navier-Stokes equation. U is the solution of the lattice Blotzmann method, which is not accurate. Yeah, it has an error. So this is, now we have to make a decision, and again, you can make other decisions than that. But this is a useful decision if you want to see convergence. Actually, for this nonlinear part, it is a necessary assumption. Okay, so you have a zero order velocity, and you can decide that you count this as being zero. And instead, you have u first order together with epsilon, and you decide not that, but that one here is your solution. Yeah, so you decide, you could make a different decision. So in practice, your decision, what your decision means is if you decide that u0 is your result, then you would keep the same initial and boundary conditions to u when you refine your grid. Yeah? When you say that u1 is your result, then you would change together with epsilon your initial and boundary conditions in order to enforce this, that u becomes smaller when you make your grid smaller, right? So this is your decision to do this. Yeah. So and now we say that for the purpose of this lecture, we decide that we choose to make the initial and boundary conditions depending on the resolution. So then we have u to the second order with epsilon square and all of the above, and we call this thing here the error. So then we now are done and can go back to our equation and do an asymptotic expansion of LBGK in diffusive scaling from the equation 8.4. And here I again have to give a message from mathematicians. So mathematician would tell you, because of the regularity problem, it's apparently so that you have to expand the populations first, and then you are allowed to do a Taylor expansion, assuming that the lower orders in this expansion and in the asymptotic expansion are regular. Yeah. So in principle, we have to expand asymptotically first and then do Taylor expansion. Now, since we have already done the Taylor expansion, I do it the other way around. And believe me, the result is the same. So I just don't go back now. Yeah. So we come to equation 8.5, where we no 8.5 basically. Okay, I write down the equation again. Yes, I write it down again. Yeah, basically it's the same. So we have the sum over everything, 1 over m factorial n factorial l factorial, delta t divided by 1/2 divided by 2, delta x divided by 2, n plus l. We have dt, the m derivative, dx, the n derivative, dy, the l derivative, and here comes now, okay, maybe I'm not completely sure. Okay, I have to look back at equation. what was our equation? Okay, so yes, it's not the same thing. So because we took the moments, yeah, of the expansion, now we have the moments are expanded like this, yeah. So we'll, we have I by the power of a plus n, right? So now we get the moment a plus n, yeah, and b plus l, yeah, clear. It's not okay, and this goes into 1 minus 1 m plus l plus n. And okay, so we had there the sum of, so we had f and f star, yeah, and then we have this changing sign for f star. So we'll have, so I've put these together, that this is hopefully, now I've just taken it from my notes, but I hope this is correct. Yeah, so this is whenever the two gets into a sum, and then we have the opposite case where we get the difference of them, right? And the difference we have identified as this omega. So I write omega, no, I get a new page apparently, but I should still write this on the same page, otherwise it looks, so it's minus omega, but so again here we have a plus n and b plus l, and with the omega I have to divide by 2 because I get this thing twice, yeah, and in the other definition I've already divided by 2, and kind of, and then we have 1 plus minus 1 by the power of n plus l plus m, which I've now taken from my notes, and I hope they are correct, but you can do as a homework to correct me. So now this is before asymptotic expansion. Yeah, so this is just the Taylor expansion that we have. And now we combine the two things with the Taylor, we do the Taylor expansion. Okay, I'll decide it in my notes that I explicitly write what I've just said. Yeah, so we do the Taylor expansion of the asymptotically expanded moments. So this is the right order as I have been told. Even though we did it the other way around, yeah. So we say that 0, now we plug the asymptotic expansion into this. It's m, n, and l is equal to 0. Also, we say that q is what we expand, where we expand the moments. The q is the asymptotic expansion of the moments. We also start from 0 and we go with all of them to infinity. 1 over m factorial, n factorial, l factorial. So now we have epsilon everywhere. And because we have acoustic scaling, the part that goes with the delta t comes twice. So we have m counts delta t, diffusive, yeah. So we have m counts delta t, so we'll have it twice. Yeah, but the others, n plus l plus q, they count only once. So q is the one from the moment, so I'll write this down. Then these this 1 over 2, right? So this 1 over 2 remains here as 2 over 2 by the power of n plus m plus L. I don't know why I put it in this strange order. Yeah, so these are 1 over 2 by m and 1 over 2 by n plus L. Yeah. Then this goes into dt m dx n dy L, and back here we'll have m a plus n and b plus L. So this is again this over bar, and here now we have Q, the Q part of the moment. Yeah, so this Q, so will expand. Yeah, so this is the asymptotic expansion. Yeah, this is epsilon times epsilon by the power of Q, and I've taken the liberty to already assemble all of that together here.
Q times 2n plus n plus L, not plus.
You mean in the exponent?
Yes.
No. So you have you have epsilon by the power of Q times this thing here. So if you put them together, you have the sum in the, so you have the product down there. So you put them together, you have the sum in the exponent. Yeah, no, so we get, so you have epsilon to m times epsilon Q. Yeah, so because this is originally here in this position. Yeah. Yeah, so and then because the equation is getting long, I want to write it as compact as possible right now, because I mean we have already 1.5 hours in. Yeah. So this is an important lecture. I don't want to, you should get everything here. Yeah. I mean, there are very funny comments on the internet on, and people have seen this lecture. Yeah, this is because it's potentially not very easy. I know. So we collect all the epsilons in front, and then we still have 1 minus 1 n plus L plus m minus omega. So there's the same thing, a plus n, b plus L, order Q divided by 2, 1 plus minus 1 n plus L plus m. All the brackets closed. Okay. So this equation, so what's next? Yeah, so we have here the series expansion, and now we use a common trick to go from a series to to a sequence. Yeah. So this you come from a series to a sequence using comparing coefficients, equating coefficients. Yeah. Koeffizientenvergleich auf Deutsch. So the idea is the following. This equation 8.5 or 8.5b, if you like, this is equal to 0. And this is supposed to be 0 for all epsilon, because we did not specify epsilon other than it is small, right? So then this will only be the case if each something times epsilon by the power of q is 0. Because, I mean, epsilon can be anything, but it's larger than 0, right? So we can make this independent of 0. I do not need to explain equating coefficients. No, right, okay. Then when we equate coefficients, we can take each of them outside. So I'll have the following sum. And now this may look a little bit strange now. Yeah, we say this mn L is equal to 0, and then we have a Q is equal to P minus 2m minus n minus L. Okay, so we sum. What we mean is we have now the parameter P that we can specify, yeah, and the sum goes from mnl equal to 0 to q being that sum here. Yeah, all of them are together. So there's no infinity anymore. It's this q always have to be the sum of these. So, and then we have again here m factorial, n factorial, L factorial. We have the thing here, this 2 by the power of n plus m plus L. Okay, we'll can write this down here. And then we have dt by the power, not by the power, the m derivative in t, the n derivative in x, and the L derivative in y. Then we have ma plus n of the order q, b plus L, 1 minus 1 to the power n plus L plus m. And then we have the omega part minus omega a plus n and b plus L. And this also to the order q divided by 2. 1 plus now minus 1 n plus to the power of n plus L plus m. All the brackets closed. Okay, so that's the absolute master equation. So from that equation we can now derive everything. Epsilon. No, there is no epsilon in this. We have done equating the coefficients. These are the coefficients, yeah? So I mean each p is a coefficient. Each p is one of the sum in this long series, right? So now some specifications. We say, okay, I've gone again a mistake here, that no, it's okay. So we specify, so because this is important for the, M and L, for the Q, yeah? So what we specify for the Q that we have only asymptotically small things. So we say that omega AB of the order Q would be the same as this here being 0 for all q being smaller than 0, right? So whenever we go into negative orders, this thing will just disappear, because otherwise we'll have infinitely many terms here, yeah? But also if we had these terms, that would mean that they would be getting larger with the smallness parameter getting smaller. Yeah, and that is possible, but if this happens, the method doesn't work anyway. Yeah, so we are now optimistic and see, suppose this is the case and the method works, then now we are like the mathematicians. We say we assume they are zero, right? And then we see whether this works. So now what we can do is we can use p equal to some value and see what happens. Yeah. So p equal to 0 is basically in this above equation. Would be all the terms that go with epsilon by the power of 0. Yeah. So and when you plug this into this equation, so you only take the ones that you can do with p equal to 0, and where all the ones where q is smaller than 1. So if p is equal to 0, yeah, everything here is negative. So there is everything else is gone, unless m and n and l is all 0. Yeah. So what you're basically left with is that only this term back here is minus omega ab to the order of 0 is 0. Okay? Now we have identified that this collision term, so this is the first outcome of this. The first outcome of this is that to 0 order, the collision term disappears. Okay? So now we go step by step. We put p equal to 1. That means we are looking at the terms that are with epsilon by the power of 1. Now what drops out of this equation is, first we get dx of m. So we don't get a dt. Yeah. So we don't get a dt because we have here 2m. Yeah. So we start with dx, and here we have a plus 1 and b of order 1 plus dy ma of order 0 a b plus 1 minus omega ab of order 1 is equal to 0. Now, again, it is up to you. It is up to you to decide whether you put non-constant values into order 0. So it's something that you don't make smaller in order 0, which is not constant. We decide, and I'm a little bit fast here, but otherwise, I mean, this is something that you can set with your initial and boundary conditions, that the 0 order moments, you put them to a constant value, not necessarily to 0, but to a constant. And when you put them to a constant and you take a derivative, they will disappear. Yeah. So if this is your scaling that you do, then what you find is that omega ab, so for any moment to first order is 0 again. So we have now proven that under these assumptions again, yeah, that omega to the 0 order is 0 and omega to the first order is 0. Okay? So now we come to p equal to 2. So meaning epsilon squared. So here's the first time we get a time derivative. Yeah, because now we can have dt mab now to 0 order. Yeah, to 0 order. By the way, we actually don't get this by the same token because we say this is 0 order, so it's constant, so it does not change in time. Yeah. So it will disappear, even though it's not necessarily 0. So that would be gone. Plus dy ma b plus 1 first order plus dxm first order a plus 1b minus omega ab to second order. So apparently that is, there are some things that are not necessarily, so yeah, this is an equation that comes out, yeah, so we cannot go further on that. What we do instead is we go to p equal to 3, which means epsilon, the terms epsilon to the power of 3. And then we see that this gives us dt MAB to first order plus dx a plus 1. See, this is the important thing, yeah? We always count up the moments with the spatial derivatives, yeah? Very important. So this will be second order dy MAB plus 1 second order minus omega AB third order is equal to 0. Okay, now we can be a little bit more specific. Now we have 3 parameters. We have the parameter 3, we have A and B, right? Now we can also decide on A and B. So we say specifically epsilon square and A equal to 0 and B equal to 0. Yeah? What will we see? So again, dt m00 to 0 order, yeah, we just say this is 0 plus dx m10 to first order plus dy m01 to first order minus omega 00 to second order is equal to 0. Now we know what this m00 is. This is the density, yeah? So 0 moment. The 0 moment is a conserved moment. If it's a conserved moment, then the difference between the pre and the post collision should be the same, yeah? Meaning that this thing here is conserved, and when this is conserved, it is 0. I mean, you have the freedom. You have the freedom to impose a source term, right? But if the source term is 0, then this disappears. So then also we know m00 to 0 order. So this is the density rho to 0 order, yeah? And we already said that everything to 0 order is constant. Okay, that's constant. Then we have m in this, we have the derivative of m110 first order. So that's, and here comes the nonlinearity into play. Yeah, we have, so you remember that m10 is rho times u. Yeah, so this is a nonlinear thing. We have u and we have rho, and together they should be first order. So if they are together to be first order, then this means there would be rho to 0 order times u to first order, right? Plus rho to first order and u to 0 order. Now, what does this mean? U to 0 order, we say, so by our initial and boundary conditions, we decide that our solution is the first order of velocity and that u needs to be small. I mean, that there's no background velocity other than 0. So by design, and we have to set this in the initial and boundary conditions of our simulation, we say that this here is 0. And then that m10 to first order is rho to the 0 order and times u to the first order. m01 to first order is rho to the 0 order v to the first order plus rho to the first order and v to the 0 order. Okay, again, this is 0. Which means all of this together go into dx rho 0 u1 plus dy rho 0 v1 is equal to 0, which by means that rho 0 is a constant, so it can always be drawn in front. So this can be written as rho 0 into divergence of u at the first order is equal to 0. So that's the first partial differential equation that we get out of this, obviously. Yeah? Okay, so this is, we call this the equivalent. So this is something that is solved by our methods. Okay, other equation. Epsilon to the third order, a to the first order, and b to the 0 order. This we are going to do this to get the momentum equation. So we'll call this thing here 8.6. And what we get out is m10 to the first order, the t derivative, plus dx. We always count up, so here's 2, 0 to second order, so we'll always have first order in time together with second order in space, plus dy m11 to second order minus omega 1, 0 to what order? A little louder. 3, right. So equal to 0. Now we have to, now we are getting stuck here. In order to go on, we have to plug the, actually, our collision operator, the BGK operator into it, otherwise we cannot go on. So we'll have we look at BGK. Again, we have MAB over bar is MAB plus before collision plus after collision. And you know that MAB after collision is MAB before collision. So this is the BGK equation. MAB, I'm going to call the BGK equation 8.7. So also we have omega AB is the post-collision minus the pre-collision. And I think I've done this already, but for self-containment, yeah, again, we can rewrite this as MAB is MA, so before collision is the intermediate minus 1/2 the collision part here, and post-collision is the MAB average plus the collision, half of the collision part. So when we do this, we can use 8.7 to do all the replacements by writing MA. So we are plugging these things here in this equation up there, right? So we have MAB over bar plus omega AB divided by 2 is MAB over bar minus omega AB divided by 2 plus omega MAB equilibrium minus MAB over bar. So there's a minus in front of this, there's a minus here, so it will become a plus omega AB divided by 2. And this can be solved for omega AB equal to small omega MAB AB equilibrium minus, okay, now it's not solved, it's just, okay, I just delete this, I just subtract the things. It's not yet solved. Yes, we can actually use this to rewrite. Okay, we can solve this for MAB over bar as being MAB equilibrium minus 1 over omega minus 1/2 omega AB. And this is something that we go back into our equation 8.6. So equation 8.6 was this expansion to third order of the momentum equation. Are you following me? I mean, sorry for the late, but I mean, this took a very long time to think up. Yeah. And it was, yes, should take a break, yes. So dt, so we now plug this in, yeah. So first of all, I plug in the moment M10, yeah. I know that this is rho 0 U1, right? And then we get this dx, and here we'll have to plug this guy here in. It's M20 equilibrium to, now it's second order, because all of this is second order. Yeah, so up there was second order. So this here is the general, and now we take only the second order part of this. And because we are doing diffusive scaling, and I'm not getting tired to repeat this, in acoustic scaling, you have to expand this. In diffusive scaling, this is a constant. So, so this is this part, and then comes omega 20 equilibrium plus dy M11 equilibrium to second order minus 1 over omega minus 1/2 omega 11 second order, and all of this minus omega 10 to third order, and all of this is equal to 0. So now this is something that we've learned. M20 equilibrium to second order is what? U square. Yeah, okay. So U to first order square, rho 0 order, yeah? Plus, so that's not all of it. We also have this theta part, so CS. And this, in order for this to be second order, means this comes with rho to second order. Yeah? So now we have rho to 0 order and we have rho to second order. Okay? And the M11 equilibrium is a little simpler. It's U1 V1 times rho 0. Now plugging this in gives us equation 8.8. dt rho 0 U1 plus dx comes theta rho second order plus u first order square rho 0 plus dy u1 v1 rho 0. And I've already taken out the other part here that comes with this what we later will identify with viscosity, 1 over omega minus 1/2. And here comes dx omega to 0 to second order plus dy omega 1 to second order, closing the brackets, minus omega 1 0 to third order, all of this equal to 0. Okay, still confused? Now we have to, you see, in order to solve this, we need to know what these omegas are, right? And they are to second order, and they are, for example, 2 and 0. Yeah. So what we can do is, in order to see what this is, we take the equation, our original equation, to epsilon to second order, a equal to 2 and b equal to 0, because this is where we find omega to 0 to the second order. Yeah. So doing this gives us dt m to 0 to 0 order, and we've already said that that would be constant, so we'll put this to 0, plus dx m 3 0. So we count up here to 3. We know this is that could be a problem, yeah, but we have done this already. To first order, plus dy m to 1 to first order, minus omega to 0 second order is equal to 0. So that means we can write omega to 0 to second order is equal to dx m3 0 to first order plus dy m to 1 also to first order. And now you remember that we are doing BGK. All the moments behave the same way, yeah, and they are their equilibrium plus 1 over omega minus 1/2 times big omega, yeah. So to first order, what did we say about omega to first order? So if I take the liberty to go back, we derived that omega to first order is always 0. Yeah? That means that to first order, all these moments are equal to their equilibrium. Why do I put an equal sign here? That's the wrong place. Okay, now it's the right place because I already wanted to write. So this means that this here is equilibrium already, right? Plus dy m to 1 equilibrium to first order. So the same, of course, is true for, okay, yes, I should probably, the reason for this being that any omega to first order is equal to 0. Okay, m30 equilibrium to first order is, of course, m10. This is an alien, as we discussed, and this is rho 0 u1. Okay? M12 equilibrium to first order is theta rho 0 u1. So there are higher terms in velocity in it, but they will disappear. Yeah, there's only this first part will show up to first order. Yeah, and we are looking at first order. Also, we have, of course, M21. This is something that we also need to first order is a theta rho 0 v1, and all of these things we put into 8.8. Yeah, so this equation up there. Which takes us to amazing page number 7. 0 is equal to dt rho 0 order u first order plus dx theta rho second order plus u first order square rho 0 order plus dy u first order v first order rho 0 order minus 1 over omega minus 1/2 into, now you see we have the first derivative, like here dx on this thing, and this on omega, and omega also is has dx and dy here. So I already pulled this together to dxx u first order rho 0 order plus dyy theta u first order rho 0 order, and I've taken the liberty of taking this mixed term out and see that this is 2u 1 theta rho to 0 order, closing these brackets, and I am kind of missing minus omega 1 0 to third order. Okay, I'm going to call this stuff up here, I'm going to call this A, and say that A is equal to rho to the 0 order. We take theta out and have the xx u first order plus dy y u first order. So what have I done? I've taken this theta in front of this, and I said I also take this here and multiply it by theta. Yeah, so there is no theta here. So I've done something wrong. So what I've done wrong, I have to correct down here. And what I have here is that if I only have to correct something here, I have dx in front of everything. So I take dx out. Yeah, dx, and then I have dx. I have dx v1. I have dx v. And I think I miswrote. It must be v here. It must be v here. Okay, so this v. So because of the time, I skipped over taking this thing here again. But you notice this will just be a different permutation of these indices. Yeah. So we have here v. We have 2 times u, and we'll have u1. Everything wrong on my script here. So you see, I said this theta does not exist. So now to repair this, I have to put a 1 and minus theta here. I still have rho 0. Plus I have this second part here, 2v first order theta rho to 0 order. And now I'll call this thing here B. Now, why am I going to do this? You see, this here is a nice part. that I would like to keep, because it's the Laplacian of the velocity u. So what's about the other thing? The other thing is something that I don't like. So I said that b is supposed to be 0. Let's look at this. What we can use, because there is a dx and a dy of u and v, what we are going to use is, we discovered that to first order in velocity, and these are first order in velocity, this thing here is 0. Yeah? So this is something that we've discovered. So the thing would be 0 if this factor and that factor would be the same. So that here would be the same, right? So the implication is that if 1 minus theta is equal to 2 theta, then this would be 0, and this implies, again, something that we of course know, is that this is 1/3. Yeah, so now we have derived this again and see why this is the case. And then finally, we can write out this equation under this conditions. We get dt rho 0, which we can write in front because it's a constant, u1 plus dx. So okay, I made a mistake again, so I have to look up here. dx theta rho second order. So this is this thing here. Yeah. Okay, no, let me write. Unfortunately, I made some mistake here. Okay, I'll try to correct it. dx. So what we are going to do? We are okay. I want to write it like in the Navier-Stokes equation. So I put the time derivative, material derivative on the left-hand side, and part of the material difference is this here in conservative form, u1 square. Yeah, so that will be u first order square rho 0, and this comes together with dy, and here we have u1 v1 rho 0. So all of this here is the material derivative in conservative form. You can also rewrite it in non-conservative, potentially more familiar form by using, again, the divergence theorem, yeah, to eliminate the other part. And this is equal, so I'm putting now this here on the other side, yeah. This is equal to minus dx theta rho to the second order plus, now I have this b term, so this is theta rho to the 0 order now, 1 over omega minus 1/2, and this goes into dxx u1 n plus dy y u1. And the one thing that's still missing is this minus. Okay, I'll write it a little bit. No, I write it here. Minus omega 1 0 to third order. So now we have the material derivative here. We have pressure here. Yeah, so pressure is theta rho to the second order. Then this here is our viscous part. And what is this? So it's the chain. This is the force, right? Yes, it's the body force. So if you have a change in momentum, you need a force. Okay? So, how much time did we run over? I guess you are completely okay. I went out of my way and thought about because you said you want to have a, you asked last time, do we have an exercise? Do you guys want to have an exercise? Do you agree? No. Okay, because I thought about something. Okay, done. Yes. Okay. So for the ones who want to see the exercise, I do an exercise. You can watch it later if you like. I've prepared something, so let's try something. Yes, so the reason why we do all of this way is because we want to automate this. Yeah. So today, no working on the code, but working with computer algebra. And of course, I don't want to make advertisement here, but this is I'm usually the one that I'm using is mathematica. In mathematica, was invented by is a program of the guy who also claims that he kind of invented lattice Postman, which is not true, but whatever. I know this was a hard session now. So let me see. It's two pages what I've written down. It's not too much. Yeah. So we did all of this in order to automate this. Let's see whether we can actually automate this. One part that I potentially, okay, what may not be completely clear when we look at our equation, our master equation, the master equation, which is this one here, yes, so this one here. What it may not be completely clear is that you can always solve, okay, so you can always solve this for the lowest order omega, and then recursively put this equation into itself. Yeah. So in order to see this, so all we do is we're implementing this equation, but solved for this omega. Okay. And this is the challenge of today, and I'm okay. He is wishing a good Christmas for us. Yeah. Okay. Let's dig into it. So we say that there is an omega, and I will now use indices. Yeah. Which I can use with as variables in Mathematica. So this unfortunately requires a little bit of technical things in Mathematica. This is also why I cannot easily do this in a different computer algebra system, because then the technicalities are different. So I say that there's a wild card, so I leave this as a changeable index. Yeah. A, B, and also I want to have my order here. And in order to distinguish it, I put it in a bracket just for, because I cannot put it up there. Yes, I have to put it here in the index. And okay, let's just call this order. And this, of course, is a function of x, y, and t. So, now, in order to simplify things, we have seen that if the order is smaller than 2, then the thing is 0, right? And only if it's not smaller than 2, we actually have to implement this equation. So the equation is a sum, and in the sum we have 1 over, now all these things, m factorial times, okay, we don't need the times, n factorial, L factorial, and times 2 by the power of, it was n plus m plus L, plus L, okay? So that's what we had in this equation. And we have to close the next bracket. So now this goes into the derivatives. So I'll take the, so what I'm going to do is I don't directly write the derivatives, but I write something that I will later replace by a function for the derivatives. I call this dd, yeah? And later I will change this. So here we're coming with the moments, which lazily I will call now MO. Okay, I know there's OM and MO. Okay, yeah. Anyway, so here again, this will have an index, and this index is now using the rules that we discovered, namely that this is A plus N. Yeah, we're counting this up, and B plus L, and then there's also an order, and this order. Now, okay, we come back to our strange equation here. See, we said that this order is P minus, okay, here we called it P. Maybe I should call it P, right? So this, yes, so that the Q here is P minus 2M minus N minus L. Okay, so let's go back. So calling this P, okay? P, so if P is smaller than, yeah? So, and then this here means, so what did I say? So this is P minus 2 times M minus N minus L. Yeah, so this is the order of this thing. And then all of this is a function of x, y, and t. And this has to be multiplied with 1 minus 1 by the power of n plus L plus m. Okay, are we still, you look in your equation that this is the right equation. Closing brackets. So this was the moment. Now comes the omega. Now we have, okay, so there's one problem. Yeah, we put omega to the other side, but we have a sum. So we have to exclude that omega from the other side, otherwise we get into an infinite loop. So the way we could do this, so first of all, there was a minus in front of the omega. Yeah. So the way I do this very simply, I write an if. Yeah, I write if n is not equal to 0 and the other one, L, is also not equal to 0, then I actually have to do something. Otherwise, I'll have 0. Okay, so here I have to do something. Yeah. Otherwise, I put it already on the other side. Okay, so now this thing that we have to do is, of course, recursion. Yeah, omega. Now it's A plus N and B plus L. And again, here we have P minus 2 times M minus N minus L. Okay? And then all of this also has to be multiplied. We have to divide this by 2 according to our equation. And then we have to multiply this by 1 plus, the other one had a minus here, 1 plus minus 1 by the power of n plus L plus M. Okay, are we still agreeing on that? 2 brackets closed. Okay, so now here is the sum. Okay, so the sum, no, before we come to the sum, we have to do the derivative. Yeah, so there are derivatives in 3 directions. So this is first is t goes to m, the m derivative in t. Then we have x, and x goes with n, and then we have y goes with L. Yeah, so these we have. So, and now we only have to do the sum, and the sum is yes. Okay, so we get, so the highest order that can appear. So actually we have to sum to infinity, but the highest order that can appear because we subtract something is the start order, the order p, right? So we can sum m from 0 to p. So we can just sum, in mathematica, we can do this, that we sum over different dimensions. Yeah, it's the same as with the derivatives. So it's n0 and p, and we also have L0 and p. Okay. So, anything wrong here? No, not so far. Okay, yes, you are right, but you know that doesn't matter. Yeah, because it will be. I mean, it will drop out. In principle, you have to sum into infinity, and just I said that this isn't over. Yeah. So if you do this to 1/2, then you have to consider whether an odd or an even. Yes, it's better to have one more. That yeah. Okay, I want to do something else here. I want to also introduce the collision operator. Where I said that the moment I need to give different names here because otherwise we have already A and B in the same function. BB and say QQ X, Y, and T is okay. So you see, when we can go with this, we can go into the negative, right? And we said that the moments for the negative are 0, right? So I say that if Q is smaller than 1, actually I should thinking about this Q. Okay, so we'll take out also the constants. Yeah, maybe I should have Q smaller than 0. Okay, let's see whether this works with Q smaller than 0. So otherwise, it will be the moment equilibrium AA, BB, and order QQ of X, Y, and T minus 1 over omega minus 1/2, and this into ohm, yeah, ohm AA, BB, and Q of X, Y, and T. Okay? So I made one mistake. If I put this 1 ohm on the other side, then I have to put everything, with a minus in front. Okay, so let's say it's, how does this work? Ohm 0, 0, say first order, okay, should be X, Y, T, that should be 0, right? So what's about second order? Okay, well, I get these things here. So the thing is, I have not specified what are my my equilibrium moments, and these of course I have to specify them. So let's go back and do this also. So first of all, I have to specify my original variable, my basic, how's that called, the primitive variable. So my rho and my u, and they are expanded, and they are usually expanded to infinity. But in order, but if I have my asymptotic expansion in a finite range, then I also have to do this only in a finite range. And for this, I'll now will say that we go up to at most 10, which is already over the top. Yeah, just to give this a number. Yeah. So, and then I call this my rho. In order to distinguish it, I put an E. I don't know why I put an E. Just my expansion probably. Yeah. So the sum. So, and here we have epsilon to the power of n times rho rho n. And this is, of course, a function of x, y, and t. And I have to sum this from n from 0 to q max. So, and I will already replace, in order for this, oh no, I make this later. U, E, the same thing, right? U, E is this just with U, and then V, E is the same, just this with V. Okay, I'm going, so this is the expansion. I'm going to put semicolon in order not to see these. So now we need our moments, our equilibrium moments, and so I give them a little bit of different names. I put an M in front of them so that I can decide myself when to replace them, right? So MEQ of the order 0, 0, and say the order Q. And this is a function of x, y, and t, obviously. And so, okay, that is, of course, so I want my equilibrium at a specific order. The way I can do this in mathematica, and I don't want, I mean, I have a mathematica lecture next semester if anybody is interested. The way we do is I'm using the function coefficient. Coefficient takes the polynomial and takes the so and so's coefficient of that polynomial, right? So because these things here are up there, they are polynomial in epsilon, yeah? So I put there rho touch screen. Coefficient rho e, and here comes epsilon, and we'll want to see order Q. So the same thing for all the others. No same cell. So first order here will be UE. So this is VE. So these are our conserved moments. We also have the others. Yeah, this is, say, 2, 0. Now they come into rho E. Now we can deal with complete nonlinearity here, right? UE by the power of 2 plus theta. Otherwise the same thing. So do this. Do this in the other direction. So 0, 2, VE. And then we have, for example, 1, 1. So 1, 1 does not have a theta here, but it has VE. Right? So you're watching that I'm not making any nonsense. So then are the third orders. So we've learned how we do this, right? So this is E is VE. Yeah, this is the not okay, it's small VE. And the other one 1, 2 would be VE times UE. And then we have the 1/4 order that is VE to second order plus theta. Okay, now we have our moments defined. So now let's see what comes out of this. So say we'll have 0. Okay. Actually, we have the ohm 0, 0. So ohm 0, 0 is 0. Yeah. That should be ohm 0, 0 to second order, otherwise there is nothing, and x, y, and t. So of course we get all of this. So first of all, what we want to replace is, so this strange thing is the substitution operation in Mathematica. So we want to replace mo eq with what we have defined, yeah, with mo eq q. So this doesn't, why doesn't this work? This, I have done this. Oh, that's not good. What's happening? Okay, something did not work out. So mo eq didn't I have a 0, 0? Mo eq to 0 c4. Let me see whether this x, y, t. Okay, so we get something. So why don't we get it here? 0, 0, because there's still an m. Okay, we have an m here. And the reason, how comes we have an m here? Here's m, there's an m. See, m has a different color. Somehow it does not accept the m. Somehow it does not accept the m. Why doesn't it accept the m? And have I mean, it's the same, but we're summing over m. And okay, so that's the real world application here. Is there anything? So I can use the last result with this percent type, and what I'm going to do is I replace dd by d. When I replace dd by d, it actually executes the derivative. Let me see whether, and I don't want to see this, and I've, okay, quit kernel. Something didn't fetch here. So I start a new kernel. Takes very long to start the kernel. And still M has a different color. Why does M has a different color? Oops. So this is okay. And this doesn't work. So something is wrong with it.
We should also specify the m in this if condition.
M in the if condition.
Because we have n and l not equal to 0 and maybe some.
No, M is the one for the time, yeah.
That's the only difference between m and n.
Yes. Okay, I was hoping that I could. It is not M. So there is an M. TMX. Is this really the only difference? T M.
Or maybe we just try and some condition for n.
This didn't change anything. No, of course not. Why should it? So this is the sum. Ah. What on earth? Okay, so this. Yeah, it's kind of not summing over M.
Maybe n starting from 0, n equal somewhere,
By the way, there's still an M, even though I replaced it by MM. So is there any M left? Maybe I did not execute this. Okay. It does not sum over M. So there is.
there's no starting point for n.
There's no starting point for M. The starting point is 0.
Oh, yes.
Ah! Maybe it's too late anyway. So the reason why we have this here is to exclude the omega if we have it on the other side. Okay, so these things kind of happen time and again, but I mean, I just don't see how it comes that it does not sum. I mean, it's summing over n, it's summing over L. Why doesn't it sum over? Ah, I know why it doesn't, because, okay. So now it sums. So, you know, there is one comma, yeah, one comma, and this, I mean, impossible to find, right? So now we have, okay, now we got this. So this stays on the recording forever, yeah? It's so we replace dd by d, by d. So why do we still have We have replaced it. Yeah, so this is okay. Now I got a few confusions in between. Let's go back to this. So we don't see anything because I wrote a semicolon. Yeah. So now these are the derivatives. So they will. I mean, if we take the derivative, they should evaluate to 0. So here we have something that apparently okay, I redo the definition because I'm not sure. Kill the kernel, redo the definition, because there seems to be something old in here. So there is still an M. So there is this M. Yes. Now I changed this to MM. Okay, let's see. I changed it to MM and I forgot one place. And I forgot another place, I guess. Yes, I forgot another place here. So, okay. So sorry for this confusion. Let me see whether this now works. Okay, now something, but there is still, if Q if okay, it's not Q. Well, yeah, it is. It's QQ. It's this Q. It's QQ. Okay, sorry. That's part of reality. What on earth is this? There's still a Q somewhere. Yes, there's a Q here. So let me see now. Okay, good. Sorry. Now we take the last result and do, as I said, DD replaced by D. So, and now what comes out is the divergence. So now we have a little bit of problem. We take a time derivative of D0. Now we've decided to say that D0, rho 0, is actually a constant. Yeah. So now I will plug this. I will plug this here in my definition of my Q0, and here I will replace my rho. I will replace my rho of order 0 of x, y, t, and all I have to do is to make this independent of an. So you see what I'm going to do is I just say this is not a function of x, y, and t. Yeah. So if it's not a function of x, y, and t, it will disappear, because when you take the derivative, it disappears. Okay. Now this was a little stronger than I expected. Wait. It should still be, there should still be a times rho. Okay, there is one thing that I didn't understand here, because it should multiply with rho 0. Okay, maybe Daniel was right and we should have stopped there. There is, so how would that be? That would be because, yes, this has nothing to do with this. The moment, okay, very obvious, yeah, so I'm stupid. So this, your analysis is only as good as you program it, right? So now, given this, right, I have to do this again, and I've taken this to, so row first order. Okay, now, yes. So what again I have is that the velocities to zero order, they should actually be zero, right? So I also have to specify this. So for example, that u to zero order, I want this to be zero. Yes, I don't want to have this. And I also want to have v to zero order also to be zero. So, and now we got these things here where row 0 is, for whatever reason, still a function of row 0 is still a function of x, y, and z. Why is this again? X, y, t. Okay, it's the reason because it also appears here. Somehow all of this is different from what okay, I know what I should do. It's not, I should not replace this in the moment, I should replace it here. That's the right place. Yeah, so I should, always deal with the stuff at the source. So that's the right way of, I don't know whether it's useful for you to see all these mistakes, yeah? So now we got this thing here. Yeah, we actually see that okay, how did I get very obviously, yes. Okay. That's strange what Mathematica does. Yeah, it puts a 0 as a name there. X, Y, and T. So otherwise, so did I make another mistake? So at least I will get a result that we expect. Okay? So actually we are not too far away from where we want to go. Say, so because this is already the first equation that we wanted to have. And then we said that we had the force x, yeah, and I do not specify this any further, is the omega 3, yeah. So maybe I should say at third order to be concise. This I should make ohm 1, 0, and 3. So this was the equation that we wanted to have in x, y, and t. And I want to replace this mho again with my defined equilibrium. Okay, so no, that's supposed to be a comma. And now we get these things, which look pretty complicated, but you see there are lots of derivatives of zeros in this. So maybe I'll do this and do a replacement of dd by d, dd by d, and here this is what comes about. Now you see we have these aliens here, yeah. So in order to get rid of the aliens, I would again go to the source and say we actually have a cyclic. Yeah, I'll cycle these indices. Say cycle A is, and because it's late, I'll just say this is if A is equal to 0, it will be 0. Otherwise, if it is odd, yeah, so it should be 0, 1. This is unfortunately, you think you could do this with a modulo function, but it's a little bit complicated, yeah, to do this. So I'll set if it's odd A, then I put it to 1, and otherwise I put it to 2, right? So this should do the job, and then I very simply write these indices here in this cycle function. And I do the same thing here. So when they come out in the overflow, they will simply return to what they had. So, okay, define this. And then we do this again. And then we have actually, you see, this is our time derivative of u, yeah. And here we have, this here is our, so these, I mean, if you're not familiar with mathematica, these are the derivatives, partial derivative in the different directions. So this is the second, so this is derivative in y, right? So here we'll have the advection part. So this again is a part of the advection. Yes, so we still have, okay, so we still have the theta in this. We still have the theta in this. So what we can do is, okay, we'll also replace the theta. Theta by 1/3. So we have the theta by 1/3, and what we can also do is, because we already know it, we can replace, okay, so what is solve? We have nu is equal to 1/3 times 1 over omega minus 1/2, and we want to know what is omega, right? So we get, oh, that's bad. Now, okay, that's bad. Then you should always be careful with the equal sign, yeah. Go on, go on, go on, go on. Okay, so that's what omega is. So we can put omega also here. Right, so, and now what we can do, if, how late is it? Oh, it's 6 o'clock. Do we want to stop here? It's, okay, we can, okay, one thing that we can try in the next line is to replace collect expand. So we expand everything and then we collect it together again, and we take again the last result, and so we know that we have this divergence is 0, right? So we can replace this d, the small v to the for the first order of x, y, and t, and the derivative would be in x comma a, y comma b, no, not like this, b, and t comma b. Okay, no, not we are not doing it like this. We want to with, okay, let's keep the b here. So if this is the first derivative in y direction, yeah, then we can and any derivative in x and in t, then we can replace this thing with minus the derivative in u. The derivative of u to first order of x, y, and t. Here comes now, it is in x, but in x it is a plus 1. Yeah, it is one more. And in y it is one less. So I say y, then it's here 0. And in t it does not, it's the same as before, it's b. So, and then we collect things in, so we want to have things in everything that comes with nu together, and everything that's, yeah, okay, let's have everything that comes with nu together. Collects called with one argument instead of 2, because I have not done a comma here. So, and let's get rid of this. And here we have our, you see, here we have the Laplace operator, yeah. Here we have the pressure term, and yes, and the rest is the advection term, and this is the force term that we put on the other side. So Now we are completely over time, but if you wonder why we do all of this, anyway, yes, we can derive the equation of motion, but what we can also do is we can go one order further, and then we get out this thing here, and now in this did I now here, yes, so right, so here you see these velocities to second order, and so the question is, and here you have a row to third order, yeah. Now the question is, if you assume that they would disappear. So we can, in order to make this a little bit quicker, we can do it at the source. Yeah, we can assume they will disappear here. And later we have to check whether they disappear, right? So say the second disappears. And this also, the second disappears. And here we would have to say that the first, okay, here we have to be even a little bit more complete. So we have to say that the first disappear, and that the third disappears. So there is a reason why the first, okay, that has something to do with symmetry, yeah? Which, because we are absolutely completely over time, we are not discussing any further. So let me see what is going to happen here. Now why do we get the same? So okay, we get the same equation again, yeah, which is not wrong. It's not what I expected. I was expecting to see 0. Yeah, but anyway, we get the same equation again, which is not wrong, so that it is possible to get to say that if we have initial conditions and boundary conditions to the second order for these terms, they will disappear. And so you see that lattice Blotzmann is that this method is second order accurate. Yeah. So, and then if you go on and look at the forthcoming next order, you will notice that this is no longer possible, that you put this to 0, because there will be derivatives of things that are of first order terms that are not 0. Okay, this was not a concise explanation, but I think we're now too tired to get through all of this. Again, yeah, I just wanted to show you that the reason why we derive this kind of methods is that we can then easily implement this relatively easily, yeah, within, this 2 hours. I don't, in a computer algebra, and let the computer algebra does this, get the equation, see the error, see what we can do to the error. Okay, thank you very much for listening for so long, and then I wish you a nice Christmas.